The sun has been a basic, strong region for us, especially of late, and it will go through a fundamental and entrancing change: the inversion of its attractive field. This peculiarity happens by and large at normal spans, denoting the midpoint of the sun-powered cycle. Has wide repercussions for us here on Earth. In truth, the sun might actually represent a serious risk, capable of causing far-reaching disruption and catastrophe for everybody in the world. The sun's attractive field is created by the development of electrically charged gases inside its interior, a process known as the sun's dynamo. Over time, this attractive field turns out to be progressively tangled and reshaped because of the sun's rotation and convective changes. Eventually, this process leads to a total inversion of the magnetic poles, with the north magnetic pole turning into the south magnetic pole, and vice versa. To understand this process, let's look at the sun more closely. The sun is primarily made up of hydrogen and helium in the form of plasma, a state of matter where electrons are not bound to atoms, resulting in a mixture of free electrons and ions. Its interior is divided into several layers, with the core at the center, surrounded by the radiative zone and the convective zone. The core is the sun's most critical area, where nuclear fusion occurs, converting hydrogen into helium and producing vast amounts of energy. Surrounding the core is the radiative zone, where energy is transported outward through radiation. In this area, energy moves slowly outward as photons are absorbed and re-emitted by the solar plasma. The outermost layer of the sun's interior is the convective zone, where energy is transported by convection. Hot plasma rises toward the surface, cools and sinks again, creating convection currents. The solar dynamo process primarily occurs in the convective zone and the thin layer between the radiative zone and the convective zone. This layer is critical because it is where the sun's differential rotation and shear flows play an essential role in generating the magnetic field. Here's something interesting. The sun doesn't rotate as a solid body. Various parts of the sun rotate at different rates, with the equator rotating faster than the poles, a phenomenon known as differential rotation. This differential rotation stretches and twists the magnetic field lines, intensifying the magnetic field. The solar cycle lasts approximately 11 years, during which the sun's magnetic field goes through a series of changes, culminating in the inversion of its poles. This cycle is driven by the solar dynamo and involves several stages. At the beginning of the solar cycle, the sun is in a state known as solar minimum, characterized by a low number of sunspots and minimal solar activity. The magnetic field is generally simple and bipolar, with a clear north and south magnetic pole. As the cycle progresses, the number of sunspots increases. Sunspots are areas of intense magnetic activity, and are associated with the development of magnetic fields from the sun's interior. These sunspots appear in pairs with opposite magnetic polarities and migrate closer to the equator over time. Around the midpoint of the solar cycle, the sun reaches solar maximum, a period of peak activity with the largest number of sunspots, solar flares, and coronal mass ejections, CMEs. During this phase, the magnetic field becomes increasingly complex and tangled due to constant twisting and shearing from differential rotation and convection. As the solar maximum wanes, the magnetic field begins to reorganize itself. The tangled magnetic field lines reconnect, and the global magnetic field slowly reverses its polarity. The north magnetic pole becomes the south magnetic pole and vice versa. This inversion cycle is facilitated by the movement and reconfiguration of solar plasma. After the pole inversion, the sun enters a period of declining activity, returning to solar minimum. Eventually, the magnetic field rebuilds, and the cycle begins anew. Presently, we are in the declining phase of the current solar cycle, approaching solar minimum. The sun is experiencing a reduction in sunspot activity and solar flares, as its magnetic field gradually reconfigures itself in preparation for the next solar maximum. This process, while natural, holds profound implications for both space weather and life on Earth. As the sun's magnetic field inverts, we may witness an increase in solar activity, including coronal mass ejections and solar flares, which could have significant effects on satellite communications, power grids, and even the Earth's climate. Therefore, understanding the sun's magnetic cycle is crucial for predicting space weather events and mitigating their potential impact on modern technology and infrastructure. Sun-based activity reaches its most extreme stage, and the sun's magnetic field is going to flip during this stage. We can expect to see huge movement from the sun that could be both perilous and enthralling. However, the sun's magnetic field inversion is not an unexpected flip, but rather a continuous interaction as the solar cycle progresses. Scientists monitor the sun's magnetic activity using various instruments and methods. Observatories equipped with powerful telescopes, both on Earth and in space, provide detailed pictures of the sun's surface and its sunspots. Instruments like the Solar and Heliospheric Observatory, SOHO, and the Solar Dynamics Observatory, SDO, measure the sun's magnetic field and its changes over time. One key indicator of an impending magnetic inversion is the behavior of sunspots during the solar maximum. Sunspots appear more frequently and draw closer to the sun's equator, showing that the magnetic field is becoming more unstable and preparing to flip. Sunspots, captivating solar features, are regions where the sun's magnetic field lines become twisted and tangled due to differential rotation. These regions suppress the convective movement of hot plasma, resulting in cooler, darker patches visible on the sun's surface. Sunspots can sometimes produce powerful solar flares and coronal mass ejections, CMEs, which release large amounts of energy and charged particles into space. When directed toward Earth, these events can disrupt satellite communications, affect power grids, and pose risks to astronauts. While solar flares and CMEs are related, they are distinct phenomena. Solar flares are sudden, intense eruptions of radiation caused by the release of magnetic energy associated with sunspots. They emit vast amounts of energy and light, often as X-rays and ultraviolet radiation. On the other hand, CMEs are massive eruptions of solar wind and magnetic fields from the sun's corona, launching billions of tons of solar particles into space at high speeds. Both phenomena can have significant effects on Earth, with solar flares affecting radio communications and navigation systems, while CMEs can trigger geomagnetic storms that disrupt technology and enhance auroras. The sun's dynamic behavior, particularly during times of heightened solar activity, greatly influences Earth and the surrounding space environment. Here's a brief overview of the key impacts and considerations. 1. Geomagnetic storms and technology disruptions. CMEs, large bursts of solar plasma and magnetic fields, can interact with Earth's magnetosphere, causing geomagnetic storms. Affected systems include power grids, where ground currents can overload transformers and disrupt power supply. Satellites, where solar particles can damage sensitive equipment, alter satellite orbits, and disrupt communication signals. And navigation systems like GPS, which may experience outages or reduced accuracy. A historical example is the Carrington event of 1859, which caused transmit systems to malfunction, with some even catching fire. Today, such an event could have devastating consequences for modern infrastructure. 2. Effect on space exploration. Increased solar radiation presents health risks to astronauts during spacewalks or deep space missions. Solar activity can also degrade spacecraft components and disrupt operations. 3. Auroras. A stunning phenomenon, the northern and southern lights, are enhanced by CMEs, making them visible at lower latitudes and offering spectacular light displays. While visually captivating, these events signify increased solar activity, which could present risks. 4. Solar cycle and magnetic field inversion. The 11-year solar cycle sees the sun undergo periodic changes in activity, progressing between solar minimum and maximum, with magnetic inversions occurring approximately every 11 years. These events are linked to heightened solar activity, including sunspots, flares, and CMEs. 5. Environmental and atmospheric impacts. While the sun's magnetic field inversion has limited direct effects, variations in solar radiation can slightly alter Earth's atmospheric conditions, potentially contributing to broader climatic anomalies. 6. Preparedness and research. Monitoring solar activity through ground-based observatories and satellites allows for the tracking of sunspots, solar flares, and CMEs to predict potential effects. Developing resilience, protecting power systems, enhancing satellite shielding, and building early warning systems are crucial to mitigate risks. The sun's complex behavior impacts life on Earth in intricate ways, from the beauty of auroras to the dangers of geomagnetic storms. By advancing our understanding and monitoring capabilities, we can better shield our technology and infrastructure while continuing to explore the mysteries of our solar system. Understanding the sun's behavior is essential not only for safeguarding technology on Earth, but also for advancing our exploration of space. As we delve deeper into space exploration, the risks posed by solar activity become more significant, especially as humans venture further from Earth. Monitoring the sun's activities with advanced tools like space telescopes, solar observatories, and satellites becomes crucial for predicting and mitigating the impact of solar flares and CMEs on human missions, especially those to the Moon, Mars, and beyond. Moreover, the sun's magnetic field and its cycles offer valuable insights into broader astrophysical phenomena, helping scientists better understand not just our sun, but other stars in the universe as well. Solar research is also critical for understanding the formation of stars, planets, and the dynamics of stellar evolution. By studying solar weather and magnetic activity, we gain a more profound understanding of the forces that shape not only our solar system but also the broader galactic environment. In summary, while the sun's behavior can present significant challenges, such as disrupting communication systems, damaging satellites, and posing health risks to astronauts, the advancements in solar science provide us with the tools needed to predict and prepare for such events. With continued research and monitoring, we can mitigate the risks of solar activity and harness the sun's energy in innovative ways, ensuring a safer and more prosperous future for life on Earth and for future generations of space explorers. In the coming decades, as technology advances and our presence in space grows, the need to understand and manage the sun's behavior will only increase. Preparing for the next solar maximum and ensuring our infrastructure can withstand solar storms will be essential to maintaining the functionality of modern societies and ensuring the safety of those who explore the cosmos. Looking ahead, it will be crucial to develop more resilient technologies that can withstand solar activity, particularly as our reliance on space-based infrastructure increases. Advances in satellite shielding, improved forecasting of solar storms, and the development of systems to protect power grids and communication networks will all play a vital role in safeguarding Earth's technological ecosystem. Additionally, space exploration efforts, particularly manned missions to the Moon, Mars, and beyond, will require even more robust protection against solar radiation and space weather. In this context, international collaboration will be key. As solar activity affects all nations on Earth, cooperation among space agencies, scientists, and engineers will be critical for developing global strategies to monitor and respond to solar phenomena. Sharing data, resources, and expertise will allow us to create a unified defense system that enhances our ability to predict, prepare for, and mitigate the impacts of solar storms. The study of the sun and its behavior also presents an opportunity for deeper insights into the fundamental workings of the universe. As our understanding of solar dynamics grows, we can apply this knowledge to improve our models of stellar behavior and even contribute to broader astrophysical theories. In essence, understanding the sun is not just about protecting our technology, but also about expanding our knowledge of the universe. Ultimately, the sun's activity remains a powerful force shaping life on Earth and beyond. Through continued research, technological innovation, and global collaboration, we can better protect our infrastructure, safeguard astronauts, and ensure that humanity thrives in an increasingly spacefaring future. By mastering our understanding of the sun's cycles and magnetic behavior, we are better positioned to harness its potential while minimizing its risks. As we continue to advance in our ability to study and understand the sun, we may also unlock new methods of harnessing solar energy more efficiently. The sun is a vast and powerful source of energy, and as solar technologies improve, we may be able to tap into more sustainable forms of energy that can significantly reduce our reliance on fossil fuels. This could have profound implications for global energy policies and environmental sustainability, as solar power becomes an increasingly central part of our energy future. In parallel, the exploration of space beyond Earth will continue to expand. The challenges posed by solar radiation and space weather will be central to future missions. For example, when astronauts journey to Mars, They will be exposed to higher levels of radiation compared to missions within Earth's protective magnetosphere. Understanding and mitigating the risks posed by solar flares and CMEs will be essential for long-term human exploration of deep space. The development of protective spacecraft shielding and spacesuits, as well as systems to predict solar storms and plan missions around periods of heightened solar activity, will be vital to ensuring the safety and success of future interplanetary missions. Moreover, studying the sun's behavior could help us develop better predictive models for other astrophysical phenomena. By understanding how our own star behaves, we can apply similar principles to better comprehend the behavior of other stars in different stages of their life cycles. This knowledge could also help us learn more about exoplanets and how they might be affected by the stars they orbit, especially when considering the habitability of planets in other solar systems. The quest to understand the sun's behavior is not just about protecting our technology or astronauts, but also about expanding the limits of human knowledge. As we continue to explore the universe, the sun's dynamic nature remains a central point of interest for both Earthbound and spacefaring endeavors. The ongoing development of solar observation tools, the advancement of space exploration technology, and the collaboration between nations and institutions will ensure that humanity is well equipped to face the challenges and seize the opportunities that come with the sun's ever-changing activity. In conclusion, while the sun's behavior presents certain risks and challenges, it also offers countless opportunities for advancement. From solar energy innovations to groundbreaking space exploration, understanding the sun's complex interactions and cycles will continue to play a vital role in shaping our future. As we forge ahead in both our technological development and space exploration efforts, the study of our sun will remain essential to ensuring the prosperity and safety of life on Earth, and for humanity as a whole in the vastness of space.